Hello and welcome. In the previous lesson, we learned about the placement of vector table, reset interrupt service routine, and initialization of .data and .bss sections. In the process, we learned how the program execution jumps to the function main, which is the starting point of any C program, and what happens after the function main returns. We also understood about the reset ISR, which handles the reset interrupt. In this lesson, we shall discuss about the external interrupts, that is interrupt 0 and interrupt 1, and implement the interrupt service routine. The pin 4 on the ATmega 328 microcontroller is dedicated for interrupt 0 and pin 5 is for interrupt 1. And change in the logic level on these pins trigger the interrupt and corresponding interrupt service routine is executed by the microcontroller if defined. Note that programmer can define dedicated ISR for each interrupt. The priority level of the interrupt 0 is 2 and for interrupt 1 it is 3. That means the interrupt hold the second and third position in the interrupt vector table. The priority defines the sequence in which the interrupts are handled if several interrupts occur at the same time. The external interrupts can be edge or label triggered. When the interrupt is configured as edge triggered, the interrupt occur on the rising edge or falling edge of the logic change. In the case of rising edge triggered, the interrupt is triggered when the logic level goes from 0 to 1 and vice versa for falling edge triggered interrupt. In case of level triggered, the logic 0 triggers the interrupt and interrupts will be triggered as long as the pin is held low. The register EICRA, that is External Interrupt Control Register A, EIMSK, that is External Interrupt Mask Register, and EIFR, that is External Interrupt Flag Register, are associated with the external interrupts. Let's look into the details and function of each register. External Interrupt Control Register A is used to configure the interrupt sense control. The interrupt sense control bits define if the interrupt is edge triggered or level triggered. The bits ISE11 and ISE10 configure the interrupt 1 and ISE01 and ISE00 configure interrupt 0. When the bits are set to 00, the logic low applied on the pin triggers the interrupt. When the bits are set to 01, any change in logic level triggers the interrupt. That means the interrupt is triggered when the logic level applied on the pin changes from 0 to 1 and 1 to 0. The value 10 configures the interrupt to be falling edge sensitive and the value 11 makes it rising edge triggered. Note, the offset of the register is 69 in hex and load store instruction must be used to read and write it. External Interrupt Mask Register is used to individually enable or disable the external interrupts 0 and 1. However, the external interrupt request bit along with the global interrupt enable bit in the status register must be set to logic 1 to enable the respective interrupt. The bit 0 is used to enable or disable interrupt 0 and bit 1 is used to enable or disable interrupt 1. The offset of the register is 3D in hex in memory map mode and 1D in hex in IO map mode. The instruction in, out, and load store can be used to read and write to the register. However, correct offset must be used with each set of instruction. External interrupt flag register is set when an edge or logic changes on the interrupt pin and will remain set until the corresponding interrupt service routine is executed. The microcontroller uses the EIFR bit to remember the occurrence of the interrupt. The bit 0 remembers the occurrence of the interrupt 0 and bit 1 is used for interrupt 1. The microcontroller clears the bit upon execution of the ISR. The software can also clear the EIFR by writing 1 to the bits. The offset of the register is 3C in hex in memory map mode and 1C in hex in IO map mode. The instructions load store must be used to read and write to when the offset 3C in hex is used, and the instructions in out must be used if offset 1C in hex is used. Let's implement an ISR for the interrupt 0. The design is something like this. The main program will blink a LED connected to the pin number 14 of the microcontroller with a delay of 200 milliseconds. This will run in an infinite loop, and the interrupt service routine will switch on another LED for 300 milliseconds, switch it off, and return. The LED controlled by the ISR is connected to the pin number 15 of the microcontroller. The diagram shows the circuit of the setup. I have connected two LEDs to the pin 14 and 15 through 220 ohm resistor. Choose LEDs of different color for easy identification. A button switch is used to trigger the interrupt. One end of the button switch is connected to the 5 volt of the power rail through 220 ohm resistor. It is also connected to the pin number 4 of the microcontroller. Pin number 4 is for the interrupt 0. The other end of the button switch is connected to the ground. When the button switch is in off state, the pin number 4 of the microcontroller is pulled to logic high. And when the button switch is pressed and released after some delay, a pulse of logic low is applied to the pin number 4. Note, the interrupt is triggered only when the duration of the pulse is greater than that of the clock signal. And it must be taken care if the interrupt signal is coming from an external electronic device. But this is not a concern for us. When generating a pulse using physical switches, we must take care of scenario called switch bounce. This is due to the physical nature of the switches. When you press a switch, two metal parts come into contact. We perceive the contact is made instantly, but this is not the case. The two pieces of metal make contact for a fraction of seconds and disconnect. This repeats for several times before stable contact is established. This is called switch bounce. It can be handled by using switch debounce circuit, which is highly reliable solution. It can also be handled by introducing a delay in software just to ignore the switch bouncing. But it is not the best solution. For me, it hasn't been a major issue, so I shall use the second option, which avoids increasing the complexity of development circuitry. I shall use a delay of 100 milliseconds in the ISR to ignore the switch bounce. Let's start with implementing the function main. The first statement in main is to configure the pins 14 and 15 in output mode. These pins are the part of general purpose IO port B. The bit 0 and 1 of register DDRB, that is data direction register B, is used to configure the pins 14 and 15 respectively. Writing 1 to bit 0 sets the pin 14 in output mode and 0 sets it as input pin. When the pin is configured as output pin, it can drive a current of 40 milliamps. The content of DDRB is ORed with 03 in hex and the result is assigned back. ORing with 3 sets the bit 0 and 1 of DDRB to 1, but the rest of the bits retain the previous value. This avoids disturbing the setting of bit 2 and higher if those are being used for some other purpose. Then the interrupt register, external interrupt mask register and external interrupt control register A are configured. I am using the interrupt 0, so the EIMSK register is ORed with 1 in hex and the result is assigned back. I want the interrupt to be triggered by the logic low. So the register EICRA is ANDed with bitwise NOT of value 2 in hex and the result is assigned back. This assignment sets the bits 0 and 1 to 0, making the interrupt label triggered. Now the infinite loop is implemented using the while construct. In the loop, the LED connected to pin number 14 is switched on by ORing the content of register port B with 1 in hex and assigning the result back. This operation sets the bit 1 of the register to 1 and the previous values of the rest of the bits are not disturbed. Then delay of 200 milliseconds is provided by calling the function delay_ms. The LED is switched off by ANDing the port B with the result of bitwise NOT operation on the value 2 in hex. This assigns the bit 1 with value 0 and the content of the rest of the bits are not changed. Again, delay of 200 milliseconds is provided by calling the function delay_ms. These 4 statements are executed in the while loop infinitely. The function main is implemented in the prog.c source file. Let's implement the interrupt service routine. The ISR is implemented in the function __int0_ISR, which is placed in the prog.c source file. It implements the logic to switch on the LED connected to pin number 15, waits for 300 milliseconds and switches it off. The statements are similar to that implemented in function main. The only difference is bit 1 of the register port B is toggled between 1 and 0 to control the LED connected to pin 15. The delay of 100 milliseconds is provided at the beginning of the ISR to ignore the switch bounce. The C compiler must be instructed that the function __int0_ISR is an interrupt service routine and must be handled accordingly. This is achieved by defining attributes in the function prototype. I have used 3 attributes, namely signal, used, and externally_visible. The signal attribute indicates that the specified function is an interrupt service routine. The compiler generates function entry and exit sequences suitable for use in an ISR. This is important for ISRs as the instruction return I, that is return from interrupt service routine, must be used to return from an ISR. Otherwise, the C compiler emits the instruction ret, that is return from subroutine, for a general C function. The AVR microcontroller globally disables interrupts when an ISR is executed. ISR functions defined with the signal attribute do not re-enable interrupts, which avoids nested interrupts. If your application needs support for nested interrupts, use attribute interrupt instead of signal. The attribute used indicates that code must be emitted for function even if it appears the function is not used. This is useful as the ISR is called by the inline assembly code which compiler is not familiar of. And it may remove the function to generate optimized executable image, assuming the function is not used in the C code. The attribute externally_visible makes the function remain visible outside the current compilation unit. We have defined the ISR and the corresponding interrupt vector. Storing the jump instruction must also be updated with the address of the ISR. This is done by replacing the reference to the function underscore underscore undef underscore ISR with the name of the ISR function. Take due care while making this change to change the correct interrupt vector in the interrupt vector table. Compile the implementation and test it working. As you can see, the green LED controlled by the main program is blinking. Now, when the button switch is pressed, the red LED, which is controlled by the ISR, starts blinking. Notice it blinks until the button switch is kept pressed. This is because the interrupt is configured to be level triggered and triggered as long as the interrupt pin is held low. Once the button is released, the green LED starts blinking again. It indicates the program execution transfers from the function main to the ISR function on interrupt and returns to main once ISR returns. With this, we come to the end of this lesson. I hope it was interesting one. In the next lesson, we have a programming challenge where you will change the interrupt sense control and test its implementation. Until then, happy coding. Thank you.